Okay, so the next speaker is Laura Greene, who's a professor of physics at the University of Illinois, Urbana-Champaign. She's a great expert in superconductivity and especially in tunneling and transport studies of novel superconductors. She's a great friend of the APS and has served it in many capacities. She's also an APS fellow. A fellow of many other things of the American Association for Advancement of Science, the American Academy of Arts and Sciences, and the National Academy. And she'll be taking on another daunting task here to tell us about deciphering electron matter in novel superconductors. So let's please welcome Laura.
Oh, yeah. Girls' Club. Okay. It's okay. I guess I should. Yeah, that's fine. Excuse me. They're setting it up now because I was still writing my talk. I think I'll be the first one to prove time reversal symmetry breaking in talks. It usually just works. And I'll also plug that my other performance, besides this one today, is Physics Songs, which I encourage you all to go to tonight. I'll be singing. Okay, there we are. Okay, good. So I've changed the title of my talk. I was in consultation with a few people, and I'm going to change the word to unconventional superconductors. By the way, we have Wolfram down the street from us, and that's my name on the periodic table. I've been working with the Center for Emergent Superconductivity that's funded through the Office of Science, the Department of Energy. I don't know why that didn't come out. Okay. I had my list of collaborators there, and for some reason they didn't come out, but I have a long list of many collaborators, and I'll just move on to the next slide, which is the outline of my talk, which is a very short history of a long historical field of superconductivity. It's good to get these things in context. And I'm going to go down here because I can't see this, and these are more important than seeing me. There's new superconductors, and I will define those as conventional and unconventional. The conventional, the standard BCS electron phonon coupled that we all know and love, and that's the only really solved problems in the many-body problem in physics. And what I'm calling now unconventional is everything else. Unconventional historically meant that the order parameter symmetry, the thing that's the wave function that gives you the gap, okay, is not the same symmetry as the underlying lattice. I'm changing that definition because everyone else is doing it, and now it means these other kinds of superconductors that have correlated electron matter. And what is this correlated electron matter? I'll be spending a part of my talk describing, in fact, what is correlated electron matter. I'll mention some of the things we know, plus some examples, and mostly conclusions here. And the bottom line is, we know a lot. And what's happened, even in the past few years, has been astounding to me that I think we're going to really make some progress in this field very quickly. Why should we study superconductivity at all? Well, it's an amazing area. It's seductive and consuming. I never thought I'd be in a field this long. Unconventional superconductivity research fundamentally is playgrounds for all kinds of physics and discovery and applications and theory and computation. And you're going to hear about a lot of that in Steve White's talk and Kivelson's talk this afternoon. And the applications are many. And as I mentioned before, this is the mechanism of conventional BCS electron phonon superconductivity. It was proven by tunneling. That is the mechanism. We don't have that yet. And this is some of the applications. SMES is superconducting magnetic energy storage. Here's turbines. And I mentioned the grid. You've seen this slide before. I've been using it a long time. George Crabtree, I think, put it together. And it's the power grid. This isn't really the power grid. This is the Eisenhower highway system, but it kind of maps it out. And we see where the bright spots are. If we were going to be using renewable energies, this is where we're going to mine the wind energy and the sun energy. But we need to get that to where the demands are, which are the coasts. And we need breakthroughs in understanding and making better superconductors if we're going to incorporate as many renewables as we need to incorporate in our grid in the future. That was identified in the 2006 BES report. And you can get all these reports off of the web, and they're really great reports. They started in, I think, 2000, and they came out every year or so. And they look at a wide variety of fields and give the history and give you a snapshot where we are and future prospects. This was very enlightening for me because this is the first time I realized how important this phase diagram is. And you're going to be very bored of this phase diagram by the end of this talk. This is where it was identified. And what we have here is temperature as a function of P, which is a catch-all for either pressure or doping. And it's ubiquitous. What we have on the right side here is a simple Fermi liquid. And a Fermi liquid is something that's described by Landau quasiparticles. Landau showed us the quasiparticles live a very long time at the Fermi level. And then Wilson and others did the renormalization group and showed that we can get low energy, zero temperature behavior. This is a fairly solved problem. We also, as I'll tell you, that what's under this dome here is pretty much a solved problem. BCX works very, very well in all kinds of superconductors, whether they're conventional or unconventional. It's really amazing. What we can't do is predict where this phase boundary is. And the other thing which this whole talk is about is this area here, which is what I'm calling electron matter. Now, as you've seen, I have to do this. Every low-temperature physics talk has to have this plot. But Camerlikonis discovered this stuff serendipitously in 1911, and it was a surprise, and we didn't know. He was trying to liquefy helium, cooled down a metal, chose mercury, and did not expect the sharp drop, and there were other predictions. And I will also say that this guy had the foresight to think about superconductivity to approach our energy challenges in 1920. The history of these discoveries were still serendipitous. Bert Matthias actually came up with many new superconductors, and he was able to classify superconductors with this famous set of Matheson's rules. Transition metals, peaks of density of states at the Fermi level are good. These are things that still hold, and these other two things held very well for the conventional superconductors, which are cubic is good, and stay away from oxygen, magnetism, insulating phases, and theorists. So this didn't help us predict superconductors at all, but it helped us classify them. And it failed completely in trying to predict the new class of unconventional superconductors. That was really a surprise. I want to tell you a few notes about the BCS theory, because the more I learn about physics, the more astounded I am at how creative and how it fundamentally changed our ways we think about theoretical physics. It originates in an attractive phonon-induced quasi-particle, and quasi-particles are the dressed electrons that float around in solids. And Bardeen and Pines worked out this interaction. The superconducting state is an S-wave pair condensate that carries the supercurrent and gapped quasi-particle spectrum. I'll say that again in the next slide. This explained all the existing experiments, all of them. And it predicted new phenomena like Andreev reflection and Josephson junctions, Josephson effect. It did not lead to the discovery of new superconducting classes. It did suggest a maximum TC due to electron-phonon coupling. And it was very successful. It wouldn't be fair if I didn't also mention in the many electron problem my colleague David Pines, who's turning 90 this year. And one can argue that this whole field of the many-body problem started with him 60 years ago. He identified electron collective modes, plasmons, and quasi-electrons that later led to the identification of Landau's quasiparticles. He introduced the random phase approximation, and that phonon-induced attractive interaction would win over the repulsive screen-Coulomb interaction. And this, he claims, led to Matheson's rules, and I fully well believe that. And there's a series of papers that go back. I think the first one actually goes back to 1952, but I'm not sure. But the number 3 of this series is absolutely worth reading, and for historical and for understanding purposes, I recommend it. Now let's go to what I consider to be the complete revolution in superconductivity, which is in 1979, Franz Douglas discovered the unconventional superconductors. This was when heavy fermion materials, which have rare earths or actinides, 4F or 5F metals in them, pretty much all of them, they have an antiferromagnetic ground state, and they have low temperature electron masses that are very, very large. Notice this interesting phase diagram. There's an antiferromagnetic phase here, but what happens up here is the electrons get really heavy. And so there's some electron matter happening way up here that wasn't identified early on. And then we have our superconducting dome. Now, these were the first truly tunable superconductors through competition between ground states. So it's that same old phase diagram. And the magnetism, for the first time, looked good for superconductivity. And the electron-phonon BCS S-wave gapped superconductivity didn't hold. And that was the first time. And there are many fascinating heavy fermion superconductors. Just to be honest, in the history, I need to talk about oxides, whether it's the prediction of strontium titanate becoming a superconductor. And then Matthias and Hammond calculated the electronic structure of barium lead bismuth oxide that led to the growth of barium potassium bismuth oxide. These were where theorists were actually helping a lot and maybe getting a handle on, can we design new superconductors? Whether they actually designed these or are serendipitous is still up for discussion, but these are a bunch of really smart guys that came up with new superconductors. And then, of course, we all know about Bedmores and Mueller and their discovering of the Cuprates, and Wu, Chu, and their group broke the liquid nitrogen barrier in the YBCO, and the highest temperature superconductor is about 165 degrees under pressure of a mercury-based compound. So everything was quiet in the 60s, and someone talked about, okay, superconductivity is dead, until Hosono came around and discovered a completely new class of unconventional superconductors. These were the iron-based superconductors, and that gave a real shot in the arm to the field. The Chinese group, Zhao, pushed this up to about 58 degrees very quickly by substitutions, and it was a very exciting time. And there's a huge amount of data on here. And I think not only did it make us look for new superconductors, if there's two classes, there must be a third, the cuprates and the iron-based, but the comparing and contrasting of these two very different kinds of superconductors is helping us understand what might be the mechanism and what's going on here. Now, this is from the original BCS report. I want to show you that there's little breaks in these axes, that in fact, if this were a linear axis, this line would be very straight. Okay? What this is temperature versus year of discovery. And this temperature is the superconducting transition temperature. And we have mercury discovered in 1911 and magnesium diboride up here in the 90s. And then it sort of looks like over here, everything fractals out. I don't look at it that way anymore. The first thing, we had to add the iron-based superconductors. So this had to change. We have a whole new class of high-temperature superconductors. Now I'll tell you how I look at this graph. And I'm not the only one. Many people look at it this way, too. I now take this straight line as the conventional BCS electron-phonon mediated S-wave gapped superconductors. This is the solved problem. Nothing else is. Okay? We know a lot, and it's two different things. And I put that little explosion here, that's where I think this started, because all of the other superconductors have a very similar phase diagram. So let's say something about these classes. The first class is what I'm calling conventional. The TC is typically less than 40 degrees, magnesium diboride. Above TC, the transport is described by quasi-particles coming from a Landau Fermi liquid. We understand that. Below TC, we understand that it's BCS electron-phonon coupled, mediated to do the Cooper pairing. We understand that too. We can describe through Landau Fermi liquid theory and the Bogoliubov-Degen equations these states. We can't predict TC, but we can describe these states. And again, I want to just say how amazing this was. BCS theory said quasi-particles are destroyed and created at that phase transition. Okay? It's a new kind of many-body particle, which is the Cooper pair. And so that really is astounding. And in my belief, what I'll end up, if I get to my conclusion, is that that's the kind of theory that we need for the unconventional superconductors. Now, here's what we have for our unconventional superconductors. Temperature is much higher, and there's the ubiquitous dome phase diagram. Typically, as I mentioned before, because I want to repeat it, on the right side is the Fermi liquid, and below TC is the Cooper pairs. And I'm going to use the same line I used in the last view graph, which is, in the Fermi liquid side and under the superconducting dome, we pretty much understand this. You might have to put in an order parameter symmetry. When you have multi-band materials, it makes it a little more complicated. But pretty much we can describe the optical transport and the thermodynamic properties under the dome. But the other regions is what I'm calling electron matter. So what is electron matter? What it is not. It's not a Fermi liquid, and it's not a superconducting phase. General definition. This one really gets me in trouble, so Steve, don't get too angry at me, but this is from my narrow view as a condensed matter experimentalist. Density functional theory works pretty well in Fermi liquid, and it doesn't work to predict the electronic structure of these states that I'm going to show you, the electron matter states. But I will say that people are trying new kinds of computation, and I'm pretty astounded at how well these things are showing that they can hand put in, and some are ab initio, putting in electron correlations to start describing what's existing. And there's some predictions of phase transitions that's happened here. I can't talk about that. I don't know enough about it, but I have been surprised in reading the papers. Another thing that's interesting that I'll mention towards the end, there's been great steps forward in theory. I won't expand much on this later, but it really appears that expanding from simple Fermi liquid theory, corrections to that is not going to be the way to go. These are really new states of matter, just like Cooper pairing was a new state of matter. Experiment. It's symmetry breaking of the electronic fluid in comparison with the underlying lattice. That's my definition of electron matter. The electrons form a fluid that cannot be described by the state of the lattice that's underneath it. There's some electron-electron correlation that's stronger than the electron-lattice correlation. And there's been some great theory on that. So a quick example of that is the electronic nematicity. This is the C4 symmetry breaking. So the lattice is C4, those crosshatches is the lattice. And the electrons are the fluid that break the C4 symmetry. And there are many, many theories that hold a lot of promise. And I'll show you one at the end. I think they'll be combined sooner or later. But what we also have from this electronic nematicity, which you can include in this, are stripes in the cuprates, whether you're talking about static or fluctuating stripes. And one thing that I want to showcase, because it's new and it really surprised me, are the charge density waves that have been discovered by Rix in the cuprates. What I'll also mention a little bit is the pseudogap. And I'll just breeze over quantum critical fluctuations, heavy electrons, and temperature-dependent charge density waves in the transition metal dichalcogenides that Amelia Morrison found. So I'll just show you how ubiquitous this is in the phase diagrams. So those little explosions of electron matter, you can see that. But here we have Frank Steglish's original discovery. These are heavy fermions all over the place here, and they all have interesting phase diagrams. One argues that uranium ruthenium-2 silicon-2 has negative pressure going on it there, but that's a really fun area, and everybody's worked on it. This is not necessarily important for superconductivity, but this is the quantum critical materials. What we do know is that above a quantum critical phase transition, it's not a Fermi liquid. Okay, what is it? There's a lot of steps forward on that, and you'll hear some talk on that today. Another example, as I mentioned, the transition metal dichalcogenides and organics. It's just all over the place. But what I'll spend the rest of my talk on is saying what we know about the high temperature superconductors. What we have here is the cuprates. Again, another one of these phase diagrams where this is a Fermi liquid here. There's the superconducting phase. There's a strange metal up here. There's a pseudogap here. And what we have in the iron-based superconductors is, again, there's a Fermi liquid over here, and up here we have electronic nematicity. And if you don't have electronic nematicity up here, you often have it down here. And what I should have described here, what this is here, These are phase transitions that we understand. That's the superconducting phase transitions. Can't predict it. These two phase transitions here are in almost all the iron-based superconductors. This first one here is always a structural phase transition. Up here, the material is tetragonal. Down here, it's orthorhombic. Very close to that, a couple of degrees, even at the higher doping, is the magnetic phase transition. That's where it goes from probably weakly diamagnetic, paramagnetic, to antiferromagnetic, and very interesting spin structures. But up here, we find a certain kind of ordering of the electronic fluid. And I'm also, this is the iron pnictides, one of the iron pnictides, and this is an iron chalcogenide. There are many, many families of these materials. I just want to say one thing, because I work a lot on predictive design of superconducting materials. And Matheson's rules, which I mentioned before, they're great. They help us classify, don't tell us how to predict. We also have great rules of Matheson-like rules for high TC materials. And we've been working on this through our center. Everybody does this. It doesn't tell you where to put the atoms. So we need another approach. We're trying to work with computation. But in the meantime, let's just go on and try to understand what's going on in the electron matter part of these really fascinating materials. So the first thing, if you look at, the first thing that we notice in these things is, what is this linear resistivity? Okay, why does this material have a linear resistivity to hundreds of degrees? What's going on here? And it cannot be completely explained by quantum criticality, but I will tell you that, Miriam Sarachik mentioned whoever figures that out is going to solve TC. And I think a lot of us were on record of saying that too, and that's really great. Some of the other things I'm going to point out are the pseudogap that we see in the cuprate, the charge density waves in the cuprate, the nematicity, which we will see, I will mention in the iron-based superconductors. So here's a figure that just points out just a very, very small snapshot of some of the electron matter that's been measured. Yes, it's a little myopic to the people I know, and I apologize. But there is a huge amount in the literature that tells us a great deal. And if anybody wants to read this reference here, with two of our speakers here, I recommend that, and it'll give you a really good overview in defining electronic nematicity and stripes and the origin of these things. The pseudogap in the underdoped cuprates has huge numbers of papers in there. There are many experiments that have found that, in fact, there is a pseudogap. It goes back to the optics with Tom Timmisk and Stat, that there is a lower density of states and there are spin excitations. And one of the things that has been going on over and over and over again is that the pseudogap, the spin excitations, all this electron matter, I'm going to repeat this at the end of my talk, they seem to really wreck superconductivity. There's a competition between these ordered phases and superconductivity, but you don't get unconventional superconductivity unless you have those phases. So there's an interesting playoff there. So there's all kinds of examples. This is a paper from Reports on Progress in Physics that shows how the pseudogap is in fact very different than the superconducting gap. This is Lorentz heat capacity measurements. There's STM, there's ARPAs, and it's just really fantastic. And what I'm mentioning here, this is really for the expert, that early on, Phil Anderson talked about his RVB spin liquid. And it might be right. And there's the Yang-Rice-Zhang theory, the people who are looking at an ARPAS, is really leaning towards that way. But we're changing the way we measure the materials, and we're identifying these things. I will go just very quickly because I'm almost done. Charge density waves in the cuprates. In the early days, we looked for charge density waves. We didn't find them. We've changed the way we do physics. This whole new RICS method, this paper by Girangeli et al. Really surprised me. They're there. Elizabeth Blackburn mapped it out. There are charge density waves in the cuprates. And in the iron-based superconductors, we have the nematicity. A nematic, this is liquid crystals, and you can get a Fermi surface distortion that also breaks the C4 symmetry. And here's an example when it was first discovered by transport, that above the structural phase transition, you can force a kind of orthorhombicity. It's also seen in the ARPAS and in far infrared, and it's also seen in capacitance stilatometry, STM, and toric magnetometry. What these are just literally clouds of electrons that fluctuate. And it's amazing. Why would at very high temperatures, and in fact, we measured that with point contact spectroscopy, we're up at 177 degrees, and all of a sudden these nematic phases start forming. Why would you have this crazy state of electron clouds fluctuating at these high temperatures? And there we've mapped out that region. And I want to say, plug one of my buddies here, Wei-Ching Li, which in fact, he not only has worked out some of these orbital fluctuations, but we're writing a paper right now to show how the point contact spectroscopy is actually a filter for the nematic phases, for heavy electron phases, for electron matter. It's specifically, he's got a quantum mechanical theory that shows how we can pick up a density of states that arises from strong correlations, that is, when the self-energy is non-zero. So I guess my time is up, so I'm going to make a couple of quick conclusions, which is, I was at this SNOMAS meeting, and I made the statement, correlated electrons, the many-body problem is the unsolved problem in physics today. It makes the Higgs look like a walk in the park, and they got it. And so the other things we want to say is that I don't think it's going to be simple quasi-particles, and we have leaders here and other people who will help us figure out what the state of matter is. And I thank you for your time. Did I go? I didn't know I went over.
Let's thank Laura for a wonderful overview. Okay, I guess we already did. So we have a little time now for some questions. If there are questions in the audience, I'll ask you to come up and use a microphone. This is a large room.
I didn't think we had questions the way you were standing up there. I thought I went over. So.
While people think of that, I'll ask one myself.
You don't have to.
You don't want one? So I was intrigued by your slide with the new rules for raising TC.
Yes.
You gave us that list, and then seemed to change gears and said, let's go on and study the quantum matter, the electron matter. So I guess it kind of begs the question, do those studies of all these novel structures in electron matter come back to help us in the, or do you foresee that helping us?
There's two directions that we're going here. Okay, I've sort of given up on theory helping us find new superconductors. That is the kind of theories that tell us that you want, competing phases. It doesn't help us design new materials, but we need to understand those competing phases. Our search for new superconductors has taken a completely different direction. We're looking at motifs. We're using computation, starting with DFT to see which phases form, and then branching off the DMFT and quantum Monte Carlo to then see which are good candidates for high-temperature superconductors. And the electron matter part is, if you start out with the parent material that exhibits electron matter, either with my point contact spectroscopy or some of these other measurements, that might be a good candidate to study and then start doping it, put pressure on it, and see if, in fact, you can get a domed phase diagram. So the fact that we're learning ways to detect and classify the electron matter will help us find if we measure that, let's explore that material further.
So you might imagine adding some lines to your list here that entries would say, if I observe matter type X, that's a good sign.
If I get the excess conductance and point contact spectroscopy in a parent compound, let's at least try to dope it. Uh-oh.
Steve. Yeah.
Here.
Unfortunately, there are no microphones that are close up. I can just repeat the question if you would like.
Yeah, just actually looking at this list, I wanted to understand what 0.5 means. What do you mean by the dielectric constant?
Okay, what I mean by the dielectric constant is that it's pretty well agreed upon that a large Hubbard U, which means strong electron correlations, is needed for unconventional superconductivity. The problem with that is once you start putting a large Hubbard U material into a lattice, it could be screened by the underlying lattice. So the low dielectric constant gives you a chance of the Hubbard U not being so highly screened.
Let me repeat the second version of the question. How do you measure the dielectric constant that you put into that rule?
This list was put together for the cuprates, and the parent compound is not a metal. So thank you. That's a very good point. So it's an older list. The iron-based superconductors came by, and the heavy Fermions. These are unconventional superconductors with metallic ground states. The cuprates is a not insulating ground state. But it's an old field. I can go on forever. I better stop. Any more questions? It's so much fun.
We certainly would welcome questions from the audience. Yes, especially there's one there. Yeah, you could try to use the microphone there.
Yeah, so in your list of definitions of a non-Fermi liquid, you also said the symmetry breaking of the electron fluid. But what kind of symmetry is broken in the quantum critical state?
I'm not sure everyone could hear the question. Could you repeat it?
The question was that I don't know. Okay, I'm not a quantum critical expert on this. All I know is that if we're talking about Nematic, the ones that I covered, and I thought about keeping quantum criticality out of here completely. I know that's a non-Fermi liquid. There's a lot of ways that people define it, and I think it's an exciting area, but I don't know what symmetry is broken. So I'm pretty much sticking to the high TC phases here.
Please, would you come up and ask the question? Yeah, go back to the microphone. That also works.
So, I think it was a great talk. But I'm wondering whether this distinction of conventional and unconventional superconductivity is always appropriate. I mean, you also had in your view graph time over TC the Fullerite superconductors, which I believe many people think is phonon-induced superconductivity. At the same time, there's believed to be strong electronic correlations, and it's certainly not easy to explain the superconductivity there within the Ashberg theory or BCS theory, or at least it's very controversial whether it is. So I'm wondering whether it's sort of these two terms. I mean, in some sense, it's conventional according to the definition of electron phonon, but non-conventional in the sense of what's the underlying state. So I'm wondering really whether this distinction is always really appropriate.
So what's brought out here, there are certain materials that are not on this red line here that, how can I call them unconventional? And that's certainly true with the borocarbides. And you can see that there's one, but that's why it's in red. So it's in red. And you'll also notice that because of many discussions with Mac Beasley, BKBO is not in red either. So all I can say is there's a lot of materials that are not simple electron phonon BCS coupled, and there's a lot that I would call unconventional. And I tried to make the colors work out, but yes, there are things that are not on that red line that I would classify as conventional, and the borocarbides and the buckyballs probably would be included in that. Although it's controversial, you know. That's my view. Did that answer your question? Yeah, sort of. We can talk more. It's a very rich field.
Okay, it's quite hard to see. Are there any more questions? One more. Would you please step over to the microphone?
Okay, not working in this area, but I'm still interested, even though there's no accepted explanation for these high TC superconductors. Nevertheless, there must be some explanation that the majority of people accept. What would be the what is the attractive mechanism that most people accept for the non-conventional superconductors?
Spin fluctuations. Spin fluctuations. And so it's often, I figured I was sticking my neck out enough here. But you go back to the early papers by Scalapino, and I think it looks like he got it right. And so the idea that the pairing would be due to spin fluctuations. And so sometimes it's been stated by my colleagues that we are trying to decipher the spin fluctuation mechanism of the high-temperature superconductors. They're all, as I mentioned, Monteau and Lazarus all show that these are all next to magnetic structures, whether they're magnetic quantum critical points or not. There's always a competing phase with magnetism. Not all antiferromagnetism, but mostly. So now I'm in trouble. Okay.
Okay, I think with that probably very controversial answer, I'd like to thank Laura again for a wonderful talk.